Okay, if we can get started. Today's speaker, I think, enjoys an almost unique, and unique in my memory, which may not be complete, distinction in that he may be the only colloquium speaker that we've had whose mother greets us every time we come into this auditorium. And what I'm referring to is a picture on the wall of Carol Jane Anger, who is George's mother. In 1928, she came to Radcliffe College only 4 years after Cecilia Payne-Gaposchkin to study astronomy here at the university. Her thesis work was on establishing the relationship between atomic hydrogen absorption lines and A and B stars, and she observed the M7 Nebula and the Pleiades, I believe, to do her thesis work. Interestingly enough, there was a newspaper article written about some of her research during the time entitled, "Girl Measures Light from Star." And it described her work on demonstrating ultraviolet emission lines in stellar spectra. I'd like to think we've come a long way, but if you watch Fox News, you may doubt that. Sorry. No politics, right? Okay. Well, I'm actually here to introduce her son, George, who is here. George obtained his bachelor's degree at Oberlin in 1964 and then came to Harvard, actually the physics department, where he obtained his master's degree in 1965 and his PhD in 1969. And George's PhD thesis was not on infrared astronomy. In fact, it was almost at the other end of the spectrum, high-energy gamma rays, which he did under the supervision of Giovanni here. And I believe George worked with Trevor Weeks at that time. After finishing here at Harvard, George went to the University of Arizona and worked with Frank Lowe, another pioneer in the field. And George and Frank did some of the groundbreaking work really on mapping the galactic nucleus of our galaxy, the Orion Nebula, and some of the first infrared measurements of planets. In the late 70s, early 80s, George returned to a collaboration with a group here on the infrared telescope led by Giovanni that flew on Spacelab 2. While simultaneously writing a proposal, as we did here, for instrumentation on Spitzer. And George was the principal investigator on the multiband imaging photometer, or MIPS instrument, on Spitzer, which George led and did some, again, not to overuse the word pioneering, but it was pioneering work on debris disks. George is currently the science lead, essentially the USPI on the mid-infrared instrument or MIRI instrument on JWST, and I'm sure we'll hear more about that shortly. I'll mention that George is the author of 4 books on astronomy and astronomical instrumentation, a member of the National Academy of Sciences and the American Academy of Arts and Sciences. He was the deputy director at Steward Observatory from 1986 to 2012. And he's currently the Regents Professor of Astronomy and Planetary Sciences at the University of Arizona. So please welcome George. He will be speaking about the most ambitious space astronomy mission to date, JWST.
Okay, thank you, Gary. It's great to be here. I remember when this had books in it, so that kind of dates me. Okay, well, I thought I would start by explaining why you want to put an observatory in a Lagrangian point. And so the Keplerian laws would say that in any orbit around the sun will have its own velocity, and so two objects in adjacent orbits don't station keep. One of them will be going past the other one, but if you have two bodies, there's an area where the centrifugal force and the gravitational fields cancel, so if you put an object at a Lagrangian point, you basically station keep. And so an observatory at any of the Lagrangian points will station keep with the Earth. And of course, the sweetest spot for that is L2, because it's on the opposite side of the Earth from the sun, so you're not trapped between the two. And it's the closest one, much closer than these, so it facilitates telemetry so you can get the data back. And that's why we're putting all our observatories, Herschel, now JWST, at the Lagrangian point, L2. So I had to explain my title to start out. What I'm going to talk about is a little bit of background about infrared astronomy, and then a little bit about recent progress on JWST, and then quite a bit about the instruments, because the instruments actually show what the capabilities of the observatory will be, and they're really quite complex and very powerful instruments. I have to contrast them with Spitzer, where, because of funding issues, we basically simplified the instruments to the kind of irreducible minimum. And I was actually kind of surprised that we didn't run out of things to do with those instruments before the cryogen ran out, but it didn't seem to happen. And then I'll discuss some science ideas, just to give you some idea of what to look for. So, in terms of the development of infrared astronomy, I started at 10 microns. 10 microns is sort of in the heart of the thermal infrared, so that's what I'm going to discuss. And the problem with doing 10 microns from the ground is there's a huge background from the telescope. There's only slightly smaller background from the atmosphere, and the atmosphere is blowing over the telescope, so that background is fluctuating. And so I liken it to trying to detect a match in a blast furnace. And so I used Photoshop to put a match in there. You in the front row should be able to see the match. And a couple years ago, I was asked to give a talk about the progress in infrared astronomy, and I made this graph, which was really shocking. I was a refugee from TeV gamma rays, as Gary said, joined infrared astronomy in the middle of 1970. So when I started, this was the sensitivity level we achieved on a 60-inch telescope at 10 microns in 1 hour of integration. We made a little bit better instrument by the end of the 70s. And I normalized that. If I had had an 8-meter telescope, I could put that instrument on, what would I achieve? And that would be these 2 points. And then I looked up the exposure time calculators for the 8-meter telescopes with big 10-micron instruments with modern infrared arrays, and I was just completely amazed. And so the problem in trying to do 10-micron thermal infrared observations from the ground is the thermal background is so huge that even by 1980 we had hit it, and there was just no place to go. So I almost, after make this plot, I wanted to dig out my old photometer, see if it worked, and apply for time. At 2 microns, it's a different story because the background is much lower, and so this is the similar plot at 2 microns, and so the background was hit with really big telescopes in the mid-90s. And so that's where you get all these stories about how dramatic the improvements are in infrared astronomy. Those are all near-infrared astronomers, not mid-infrared astronomers. And of course, the solution is to go to space, because there you can cool the telescope down. If you try that on the ground, everything will condense on the telescope, and it just doesn't work. This is Frank Lowe's sketch that led to Spitzer, and the idea behind this sketch was you could do the cooling radially to space. And this was the breakthrough that allowed us to get Spitzer. And the virtue of going to space with a cold telescope is the background is about 10 million times lower than it is on the ground. And, oh, that's a lot better, isn't it? Okay. But with Spitzer, we were so worn down from years of trying to sell this mission that rather than taking advantage of Frank's idea to make the mission more grandiose, a bigger telescope, we said, look, we can keep this telescope the same size, but we can make the observatory much smaller, and look at the gains that we made, particularly in this line. And it turns out that was actually critical. I had a funny interview with Dan Golden. I was in a long line in New York for taxis, and there was a guy with a rather obnoxious voice behind me. And I turned around, and I saw these imitation alligator hide boots. And stuffed into those boots were Dan Golden's feet. And so I asked him, because I was really interested well, after all the effort we went through to try to get sort of sold, what was it that caused you to approve it in the end? And he said it was two kids at JPL came up with the idea of the warm launch. Well, Frank Lowe wasn't exactly a kid, but I got the message. It was the innovation that was something new and different rather than selling the same mission over and over again. So here is, to me, a really astounding graph. There's a metric that was used in the Bacall report for the power of an infrared telescope. It's basically, in a given amount of time, how much sky could you survey per pixel to a given sensitivity. So this is sort of a speed metric. And so here are the 3 points back in the 70s. This is IRAS, this is ISO, and this is Spitzer. And you think computers have gotten better over time. Look at this, a 9.5-month doubling time. It takes 2 years with computers. And so that is why infrared astronomy has gone from a funny little sidelight that only eccentric physicists practiced to kind of front and center in what's going on in astronomy. But the problem is, to make a cold telescope in space, the conservative thing to do is to put it inside the cryostat. That limits the size. That's why even Spitzer was 85 centimeters, because originally it was going to be inside the cryostat. And when Frank came up with this idea that we could cool it without a cryostat, we were too timid to take advantage of that. And so the telescopes have always been down here less than a meter in aperture, so the resolution has always been not very good. JWST is going to fix that. And so we have to remember it's not only a huge gain in sensitivity, but it's a huge gain in resolution. And so Spitzer, I would argue, was limited by resolution more than sensitivity. At 24 microns in 10 hours or so, you could reach a hard confusion limit against distant galaxies, so it wasn't even a function of where you were looking on the sky. And so just to dramatize that, this is a Spitzer view of JWST, and this is what the resolution does for you. I once gave the analogy that it's like going from a 300 kilopixel digital camera to a 16 megapixel camera. It's a really dramatic improvement in resolution. And so you have to keep that in mind when people show you sensitivity plots like I'm doing here. It also continues the 9.5-month doubling time. And not entirely coincidentally, this is when I entered the field. And so it's been really exciting. And of course, I had nothing to do with very little with IRAS, nothing with ISO. Other people have provided all these great gains, but this is why infrared astronomy has gone from a sort of obscure sideline that at one point there were like a dozen infrared astronomers in the universe, and now it's sort of front and center in terms of plans going forward for astronomy as a whole. But it isn't easy to do that. the entire JWST satellite has to weigh about 1/3 the weight of just the tube of our 90-inch telescope. And so there are huge challenges in building something. And of course, there's a little detail that the mirror is bigger than the rocket fairing. So you have to fold everything up. There's just a lot of engineering challenges as well as the technical challenges of just making the mirrors. Beryllium mirrors have been made to a completely new standard of quality to go with JWST. The instruments, the cryocooler. But just keep in mind this analogy. This is a big deal from an engineering point of view to build something this big that is this lightweight, and it's driven a lot of technology. But it's nearing completion, and Charles asked me if we were going to launch it before this talk. I had to chastise him a bit, but you should understand that much of your understanding of JWST, if you have a long memory, was from the era when it was being sold as an unrealistically cheap mission, and it was re-baselined about 4 years ago. And since then, it is held to schedule and budget completely. And so there was this period when Goddard managed to sell something sort of in a back alley. It wasn't, it was really nothing that was practical. And that was a huge political liability. And it was a huge psychological liability for us and for everybody in the astronomical community. But once we got through that and got a realistic budget and schedule, I have to give the managers a huge amount of credit. They've been able to deal with all the setbacks and so on and go with a big project like this and kept us on schedule and preserved our schedule margin. So we are on schedule and we're within budget. And these are I'm going to show you some of the major items of progress that have occurred just this year. So here's the instrument package. To put a scale on this, is probably about 15 feet across. Has all 4 instruments in it. And in February, this went through its 3rd and final cryogenic test, and everything works. So we're ready. The instruments are all ready to go into space. And you can just get some vicarious view of how complicated this is. And let me tell you, it's a lot more complicated than that. These instruments are when we get to the instruments, you'll see how complicated each one of them is. So it's a tremendous accomplishment that the telescope, the instruments are ready to go. Almost at the same time, the telescope was finished, and you can watch it. So each of these is a beryllium mirror that's a little over 1 meter across. They have covers, and they're being assembled onto the telescope. So you're watching the highest technology telescope ever built being in its final assembly. When I look at this, I say, geez, if I could just get my graduate students to work this way. So these mirrors required building a new plant at Tinsley and building new machines and developing a technology that was about 2 orders of magnitude more powerful in figuring beryllium mirrors than went into the Spitzer mirror. And so again, this structure is a carbon reinforced plastic structure to be super lightweight and to fit within the rocket fairing. These are the side panels that fold up, just to give you an idea of what you're seeing here. And there's the most challenging thing about the spacecraft, it turns out, is the sun shield. And it's central because the sun shield has these multi-layers, and the idea is this one blocks the sunlight, but it gets warmed up and the heat is radiated out through the gap. And so there's a little less heat here, and you go through these 5 layers, and you end up that the back of the sun shield is about 90 Kelvin, just by passive radiation to space. But this doesn't work if these gaps close up, and this sun shield has to be untethered and pulled out with cables on pulleys and so on. And there was a lot of suspense of whether these gaps would open up and the sun shield would actually work. And you can see for yourselves, it did. And this was absolutely critical for the performance in the mid-infrared, where the 90 Kelvin or a little colder sun shield temperature is essential. So this is my countdown to launch. It's not exactly seconds, but these are sort of 10 critical things that have to be done. And we're down here. We have to finish the spacecraft. We have to do an end-to-end telescope test. And then we have to integrate the telescope and the spacecraft, and then we get to ship it to French Guiana, which isn't the best vacation spot, so I'm not sure everybody's going to go to the launch, and it gets launched. And probably the most interesting test we have to go through is the end-to-end test of the telescope. This is Chamber A at Johnson Space Flight Center. It was built to test lunar rovers in. And if you hunt, you can find a picture of a lunar rover running around inside this chamber. It says it's been used as a satellite test station for NASA. You get an idea of the scale here. And so, in early 2017, it will look like this. Ooh, this is almost time travel. This is a test article that looks just like JWST. So the project has actually had a couple of full-scale tests in this chamber to get ready for the JWST test. And you can see even JWST is easily fits within this chamber. And this will be the critical test that we learn painfully with HST we need to do before we launch something. And so we're supposed to launch in October of 2018. And so the launch, we will cruise out to L2, and then there will be a rocket burn to stop us there, and we'll go into orbit around L2. And we will do most of the checkout during this cruise phase. So not too long after we get to L2, we'll start taking astronomical observations. We, I mean all of us, right? Not just those who have worked on the project. So that's sort of a quick overview of the telescope. And I want to give you a little more detail about the 4 instruments, because the purpose of my talk is to get you thinking about science you should do with this wonderful new instrument that we have. And to understand what you can do, you have to really understand the capabilities of the instruments. So let's start out with NIRCam. So NIRCam uses 2 detector types. One goes from 0.6 to 2.5 microns, and the other one goes to 5 microns. There's a dichroic mirror that separates the light. So the short wavelength and the long wavelength view the same position on the sky. And then it has the fields of view are 2.2 arc minutes, and it has some other modes, which I'm not going to discuss in great detail. But the first thing you see, this is a really complicated, sophisticated instrument. It's just not just something you take snapshots. It has a lot of capabilities. It's actually 2 identical instruments because it's also used for the wavefront sensing. And so we have redundancy in that critical mission capability by having 2 instruments that are identical. So they're 2 by 2 arc minute fields of view. There's what it really looks like. And so it's completely optimized for very deep surveys. So in one exposure with NIRCam, you'll get these 4 images, a short wavelength pair, a long wavelength pair. The scale, this is Nyquist sampled at 2 microns, this is Nyquist sampled at 4, so the full width at half max of the point spread function is twice these numbers to give you an idea of the resolution. NIRSpec is provided by ESA. Very complicated instrument largely because it has a multi-object spectral capability. Here's the real instrument. Those CAD drawings leave a lot out, don't they? So here are its basic capabilities. The multi-object lets you, they're 0.2 arc second wide slits, and a spectrum will look sort of like that. There's an IFU, and then there's a standard slit. So many different kinds of spectra. The low resolution spectroscopy goes down to 6,000 angstroms. The other spectral capabilities are 1 to 5 microns. And so there's lots of different kinds of science that this spectrometer is designed to carry out. NIRIS, near infrared imager and slitless spectrometer. Good going, George. This is what it looks like, supplied by Canada. This is what it really looks like. It has a number of capabilities. It has a slitless grism. It really has two. So you can take orthogonal spectra. So if you take an image without dispersing the light, so you know where the sources are, and you take the orthogonal spectra, then it greatly expedites actually extracting science from the spectra, given that you otherwise will have sources with spectra overlapping. It has a non-redundant mask, and this is basically you mask the telescope so that you have as many different interferometer baselines as you can get over the size of the telescope. And because you're using interferometers, the resolution is in principle twice as high as the full width half max of the point spread function from the full telescope mirror. So this is a way to take images at greatly reduced efficiency, use a lot of light, but get high contrast very close to a star, for example. And then the slitless spectrometer part of it is to optimize for planetary transits. All those instruments are cooled by just radiating passively to space, and here's one of the radiators. And they all operate basically at 40 Kelvin. So this is sort of the embodiment of the realization that was exploited in Spitzer, that you could get to 40, 35 Kelvin if you design things properly by just radiating to space. You didn't have to bring a cryogen along. Then there's the mid-infrared instrument. This covers 5 to 28.5 microns, all in one instrument. And this was basically designed and built by committee. Look at this. Nobody believed this could be done from a management point of view. And I discovered there is a secret to doing this. You threatened this instrument with being taken off the mission for the first 6 years. And everybody learns to work together and never reveal any problems to the outside world. And lo and behold, this instrument was actually delivered a year ahead of the other instruments. So it's a very effective management tool. Here's what it looks like in real life. But this instrument has to run at 6.5 Kelvin, so it has to have a cooler. And it's a very complicated cooler. It has parts in the spacecraft. It has a connection through this tower assembly that holds the telescope of the cryogen line or cold gas line. And then there's a heat sink at the instrument. This turned out to be a really difficult technology development problem. And only 7 or 8 months ago was it clear that Northrop Grumman would be able actually to build this cooler. Just to show you how it works, you have a compressor in your refrigerator, in your kitchen. It has cooling fins that cool the compressed fluid down. There's an expansion valve. And then in the freezer compartment, you have the heatsink assembly. And then you come around. And you know, this cooler is basically the same thing. There's a compressor in the spacecraft. You cool the working fluid. There's a pulse tube, a couple of pulse tube coolers. You get 18 Kelvin gas. You have a Joule-Thomson expansion valve and then a heat sink on the instrument. This is all surrounded by a heat shield. So if it's like the refrigerator in your kitchen, why did it cost $150 million? Because it has to work in space. It has to be very efficient. And it has this complicated interfaces going from the spacecraft out to the instrument. So as the only instrument from 5 to 28 microns, MIRI has to do everything. So it has an imager, has 4 coronagraphs, it has a slitless low resolution spectrum that prism that can be used slitless for planetary transits, and then it has a whole separate module that has a spectrometer with a resolution of the order of 2,000 to 3,000. So, those of you who are used to Spitzer, what's different here? These are really complicated instruments with all kinds of versatile science capabilities. And so, this is like the observatory that most directors refuse to support. They say you shouldn't have so many instruments. It costs a lot to change instruments. Since you can't change instruments, they're all packed into that structure that I showed you that we just finished testing in February. But there's just a lot of things, a lot of different science goals that you can achieve with this observatory. And now I want to just run through some examples. And I wanted to start by basically highlighting the things that you do with infrared astronomy and give you an example from each one of those. So basically, infrared astronomy is good for the high redshift universe, since all your optical astronomers have to look in the infrared for the features you're used to. The obscured universe, where there's too much dust to see what's going on, molecules, their emission is dominant in the infrared, and cold. Things that are cold radiate preferably in the infrared. And so we'll take examples from those. Before we get too deep into that, though, I want to show you the timeline, and I want to panic you just a little bit about the timeline. So the guaranteed time proposals have to be turned in just 1 year. Then there will be an opportunity, which is not on here because it hasn't been officially adopted, for what they're going to call early release science, where they want teams to propose for significant programs for things that demonstrate the capabilities of the observatory and at some level test it scientifically. And that the opportunity for that will probably be announced in the middle, maybe June of 2017. And then the general observer deadline is February of 2018, with a call for proposals kind of in September or August of 2017. So, and I've warned you, we're holding schedule. So don't count on us having a launch delay. This is really the schedule at this point. And so it's time to really think about what you might want to do. And my warning is the capabilities of this observatory are so far beyond what you're used to thinking of that you're not going to come up with the best possible idea just in a week. And that's particularly true in the thermal infrared, where I showed you that basically our capabilities from the ground, with a similar level of sophistication of instruments, spectrometers and so on, but the sensitivity hasn't changed in, let's not even go into how many years. And so you really need to get a good head start on thinking of how you will use this. And it's particularly true because right now, to do good astronomy, you need to do a lot of preparation. You need to build a team. You have to do a lot of analysis, simulations, and so on. It doesn't come quickly. Okay. We used to be the first light machine, and somebody picked this up. BBC special, you can get the DVD for First Light. And I like the Telegraph review, First Light, something both beautiful and intensely dramatic. But we have to look for it. And so this is basically what NIRCam was laid out to do. These are the two NIRCam fields of view. This is the traditional HUDF, and this is the infrared component. This is the Chandra field. So this is Chandra deep field south. This is goods. So this is sort of the prime area to go to very deep fields. And you can see that NIRCam can do a very good job of boring into the sky over sort of the heart of this area that we put so many resources in for deep surveys. This is, if you have two pointings with dithering, this is sort of how the sensitivity will look. I will show you there's a kind of embarrassing problem that high redshift galaxies do not have spectral lines in the 1 to 5 micron region. And of course, they don't even emit short of 1 micron. So the only way you're going to be able to identify first light galaxies is from photometry. So you need lots of photometric bands. And so NIRCam is designed to very efficiently give you lots of bands. That's why the dichroic is there. And the idea is to observe in 8 different bands going from 0.6 microns out to 5 to hopefully identify candidates to be first light objects. And this is, Marcia prepared this plot a long time ago. I think she now has to move this out to a higher redshift. But anyway, this sort of shows you the sensitivity you will get in that survey relative to the continuum. You're hoping for a dropout over here, but you'll be able to, these are 10 to 1 signal to noise points, and you'll be able to characterize the spectral energy distribution accurately. And that's what you will have to use to demonstrate that you have a first light object. These are current capabilities in terms of sensitivity. So you can see what a big change there is. Now here's the hard part. This is the recently announced Z of 11.1 object. The redshift is based on this dropout short of 1.6 microns, and the refined redshift was based on a low resolution sort of photometric grade spectrum that demonstrated that's really what was going on. So if you find an object like this, MIRI would be able to get points out at 6 microns, which is sort of important because this is the 6,000 angstrom break, Balmer break. And if you want to prove this object is young, this break shouldn't be there if it's really young. But if you want to get a spectrum, well, you're fighting nature here because the blue spectrum is solar metallicity. And that's what's plotted here, which is kind of dishonest because this object should be very low metallicity, and the red spectrum is 5% of solar. And not surprisingly, you can see that the line that you might want to detect with near spec on JWST gets very faint relative to H alpha. And so the best shot at actually detecting an emission line in one of these objects is with a heroic integration with MIRI. And I just did a comparison. I mean, the atmosphere blocks the wavelength you'd want to look at, but the sensitivity of MIRI to this line is about 700 times greater than the best performance ground-based spectrometer you might choose to use. But maybe there's another way. Predictions of first light objects, meaning objects dominated by population 3 stars, are that they aren't all going to be out there at redshift of 14. There should be a distribution, and there should be some of them down at maybe redshift of 7. And there are actually a couple of candidates. And so this is something dubbed Himiko, which is, I think, a legendary Japanese queen of some sort. This particular object has all the character, as far as we can tell, of being a first light object, even though it's a redshift of 6.6. So we might be able to actually understand the physical nature of these very young objects by finding some lower redshift analogs. So it's maybe hopeful getting a spectrum, just not a spectrum at redshift of 14. Okay, let's look at another science program, AGN evolution. So we all know this plot. The question that I want to pose is, for quasars at redshift of 6, we don't know how you could form the black holes, and we have even less idea of how you could form the galaxies fast enough to have a black hole with a mass of 3 times 10 to the 8 solar masses and the galaxy that should be, 500 times as massive around that black hole. So if you are going to form a galaxy that massive as fast as is required, then it has to have young stars, and those stars have to have a very large luminosity to mass ratio. And if you run the numbers, it turns out that a very high signal-to-noise spectrum, and this is a composite quasar spectrum of local quasars, that it happens the 4,000 angstrom break falls in a very well-behaved region of the spectrum. And if you add in the projected galaxy with the right luminosity to mass ratio, you should see a Balmer break in that galaxy, just brute force taking a spectrum. And so from this, you can constrain the stellar population. But better than that, there's enough spectral resolution that you could actually measure the velocity dispersion of the stars in this galaxy around a very high luminosity quasar at redshift of 6. So that's a really neat way to find out if the galaxy is really formed according to the Lagrangian relation that early in the evolution of quasars. And just as a comparison, I'm going to keep putting up these little blue explosion things to show what a big advance is required to do this. Mossfire has the sensitivity, but it's 50 times less sensitive. And so this is really out of reach for a ground-based instrument. Here's another thing that you can do. And I realize there are a lot of X-ray astronomers out there, so I have to watch my step. But you'll see why. There are a number of mid-infrared fine structure lines that are indicative of very hot, exciting spectrum from an AGN. I want to call your attention to neon 6, 7.65 microns, and it has a lot of really good properties for identifying AGN. The ionization potential is 158 electron volts, so way outside the range that stars can excite. It has a high critical density, very low interstellar extinction, and nebular models show its ratio to the hydrogen line strengths is virtually independent of the ionization parameter, and it's not readily confused with hard X-ray binaries, which is an issue with, for example, new star spectra of galaxies where you're looking for really faint AGN buried in the galaxy. So let's see what we could do with JWST to try to solve the problem. You know, everybody would like to have AGNs get born in ultraluminous infrared galaxies because there's so much happening there. There should be stuff falling in toward the nucleus, and it's just a very popular theory, particularly with theoreticians, but very hard to prove. And in fact, there's a recent paper with new star data that sort of got mixed results on this. So let's see if we can improve on that with JWST. 1 hour with JWST could detect an AGN in the center of ARC 220, sort of the most dramatic ultraluminous infrared galaxy, at a luminosity of 10 to the 7 solar luminosities. This is 10 to the minus 5 times the luminosity in young stars. So that's a pretty definitive measurement of whether there's even a very weak AGN buried down in there. Neon 6 is less affected by extinction than even hard X-rays. This is a paper that compared oxygen 4 fine structure line with integral measurements of X-ray, of AGN, and it shouldn't be excited by some of the things that cause confusion with hard X-ray measurements. So this should be the definitive test of the theoretical models that say AGNs start their lives in ultraluminous infrared galaxies, interacting galaxies. And so this is where I argue you can do better X-ray astronomy with JWST than you can with Chandra. And in fact, if you run the numbers, it's at least 2 orders of magnitude more sensitive than new star toward an obscured AGN. So now I want to show you another dramatic advantage, which is very simple. JWST is above the atmosphere. And if you want to look for biologically significant primitive molecules like water and organic molecules and so on, you want to look in heavily obscured star-forming cores. And if you want to do it from the atmosphere, you know, Mother Nature has a very cruel sense of humor because the gray here is the atmospheric transmission. So here's the 10 micron window. Here's the sort of 20 micron window. And the 10 micron silicate absorption is here. And the 18 micron silicate absorption is here. So the interstellar windows are here and here. Wasn't that mean? I mean, you go a heavily obscured star-forming core, and between the interstellar absorption and the atmospheric absorption, there's almost no spectral region that you can actually look unobscured. So being above the atmosphere is the third big advantage JWST has. And, whoops, we went down too far. Here is a simulated spectrum that Klaus Pontoppidan did of, basically these are all water lines, but this is what you would expect with a JWST spectrometer, looking in a star-forming core. And there are some hydrocarbon lines in here also, so very rich spectra and uncontaminated by the atmosphere and unobscured by the interstellar medium in these cores. Okay, exoplanets. So this was a statement that this guy made on TV about a month ago. I thought it was kind of cute. But I put it up here because we shouldn't be doing exoplanets to study the weather on exoplanets. For goodness sake, we have enough trouble understanding the weather on our own planet. Why do we need 100 more? We want to find out something much more important in a sort of physical, astrophysical sense about the exoplanets. So you all know the technique. You look at transiting planets and planets going into eclipse. Here you get a transmission spectrum, which also includes the transmission of the planetary atmosphere. Here you get an emission spectrum. And I gave a talk a while ago to Senator McCain, and I thought I would get his attention. You can actually, if you find the right planet, you can monitor global warming by looking at the CO, the carbon dioxide absorption in the atmosphere of that planet. He was sort of stone-faced through the whole thing. So you can get it. Both of these events give you information about the composition of the atmosphere. And so let me show you what you can do with that. So within the solar system, there's a trend between the metallicity of the planet, as judged mostly by observing methane, and the mass of the planet. And this was in a paper which announced the metallicity measurement for this one exoplanet. And not surprisingly, this trend is thought to arise because just by the ratio of hydrogen that gets assimilated into the planet versus heavier elements that get assimilated. So if you look at a cross-sectional drawing of Uranus and Neptune, they have rather thin, relative to their cores, hydrogen, helium atmospheres, and that's sort of a reflection of what's here. But this is also the critical constraint on planet formation models. And, you know, planet formation is a really chaotic process. And so the models right now have a sample of one to try to model how this works. And to really understand how giant planets form, you need additional examples that show either that metallicity, this is a universal trend of mass versus metallicity for planets, or there are big exceptions to that. So Tom Green and Michael Line have been running simulations of JWST observations of transits and eclipses. This is sort of in the zone that when you have a number of cases of wine in the cellar, you drink more wine than when you don't have any. At Ames, they have major computer power, so these are very complex simulations. And the result is, and they've been simulating individual examples because we know enough about transiting exoplanets to do that. And so in some cases, we can get quite accurate metallicity measurements by measuring transits and eclipses of exoplanets. In some cases it doesn't work, but there's enough that when they simulate individual known transiting planets, and that's these arrows, if they're following the solar system relation, you will get numbers that fall with errors. I mean, if it's 1,000 CPU hours, it must be right. Anyway, quite good errors. They claim that the errors here are not very different from the errors in our own planets, which is telling you that the systematics are sort of the dominant term. And so in particular, accurate measurements can be a test of core accretion models, since those predict the size of the core that would form in the planet relative to the hydrogen-helium atmosphere. So we can really test fundamental models of how giant planets form. So that's it. So here's my summary. We're getting there. Don't assume that you can just postpone thinking about JWST. And it is an amazing feat of engineering and management, and particularly management. I really have to give the managers a lot of credit. And as astronomers, we ought to be grateful that people are willing to lavish this resources on us. But I want to warn you that there's so much new capability in this mission. It takes a long time to actually think of things that are something other than just the next logical thing to do in what you're already doing. And we also know that in modern astronomy, you have to build a team, you have to develop computer tools, you have to do simulations, you have to develop theory. For a really successful proposal, there's actually a lot of work and it takes a lot of time. So I would urge you, I assume you've been delaying. So don't delay any longer, that's my message, and start thinking about how to use JWST.
Thank you so much, George. That was great. I have a question of a political nature before I hope there'll be a lot of questions of a scientific nature. But you're in a somewhat unique position, having been involved in JWST through the many years of turbulence and now achievement. And many of us are now embarked on studies for the next decadal. And a number of the missions, or certainly the optical mission, makes claims that it is just proposing another ring of mirrors around what JWST has done. And I'm just wondering if you are as sanguine that it is that simple.
Of course. Well, I keep saying JWST in my mind is about as complicated a project as I think human beings can handle. In other words, it really is amazing, all the different technologies, all the management challenges. So I'm actually worried that building a bigger telescope to tighter tolerances, that's certainly part of, it isn't just another ring. It's a better ring around a better telescope. And a more complicated unfolding scenario because it's bigger and the rocket fairings are going to be the same size. So I'm really worried about it. And you said this is political. There's sort of an ebb and flow of astronomy fortune politically. And I sort of fear that with JWST, we will have filled up the tolerance for really huge projects for a while, and that politically, a number of smaller missions might be a lot easier to push forward. So that's my answer, but don't quote me too widely because there's some areas.
You're on film, so you're already too late.
So the guided missile is on the way.
Yeah. This is live streamed to the Space Telescope Science. Okay, let's throw it open to questions for George.
There they go.
Given the large number of steps, over 100 steps that need to all successfully happen in order to successfully deploy, what is being done to try to maximize the chances that that will happen successfully?
So I could have shown you a deployment video, but I've learned that when you show that to a large number of people, half of them are inspired and half of them are terrified. And neither half has any basis for their view, so I cut that out. The history of failures in space missions is that the failures almost always occur in the low technology part. So there's one notable exception, and that's the HST mirror, and that's almost the only exception to this rule. So all the things that you're worried about, everyone's worried about, and they get a lot of attention, a lot of reviews, and so I'm quite confident that will work. And in fact, the prime contractor, Northrop Grumman, says this is only the 4th most complicated deployment we've done, but we can't tell you about the others. So we have to take their word for it. But I think that part will work. I'm more worried about something that just got overlooked because it was in the realm of normal engineering and therefore did not get the high level of attention that goes with the things that people like you say, how do you know it's going to work? Okay, there was a question.
Could you comment on something about, the Spitzer had a lot of survey programs where they essentially would kind of blanket observe.
My ears are not as good as they used to be.
Spitzer had a lot of very large observational surveys, say, for the young stellar regions. Is this something that is really capable with JWST, something we focus on, or a more individual project?
I still didn't quite.
Oh, sorry. Do you think there are going to be a lot of large-scale surveys?
Oh dear.
Good question.
Repeat the question, and
So, you have the same problem I do, right? So the question is large-scale surveys. And the answer is no. To expand on it a little bit, because JWST is so big, it's very lumbering. And so the overheads are much bigger. Spitzer was wonderful. It was, just boom, 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 3-minute slew, next object. And so the era of surveys is behind us until W first gets up there. And so you have to view JWST as, would you do large-scale surveys with Keck? Maybe not. And this is sort of the Keck of in space in that regard. And so this is a reason to, again, to think ahead, to put together some sort of idea of what you might want to do, and then check, even with a prototype planning tool, and see if the overheads really make you feel good about it, or if it's really not feasible with a telescope that takes so long to repoint.
So this is a counterpart to that question. How about a deep field? Because the Hubble deep field has been enormously revealing.
So we're great for deep fields, right? They don't move around on the sky. So
is there a plan to do a very deep field?
Yes. So the only plans that exist right now are guaranteed time observers, and the NIRCam and NIRSPEC teams are talking about, I showed you the footprint, but it went past pretty fast, a deep field centered on the HUDF. It would be 2 NIRCam pointings and then follow up NIRSPEC spectra. That is a tiny fraction even of the goods field. I don't know if you look, but so there will be GO programs to do deep fields, and yes, the efficiency is very high if you want to do it for deep field. NIRCam is, you have to do the 4 filters in the 2 bands, but they're planning to spend something like 70 hours per filter per band, so it's going very deep. I'm on the NIRCam team, but I'm at risk of getting thrown off because I keep telling them you're going to detect fuzzy little objects that no one will ever see again. And that's a real problem, is, you can go so deep how do you follow up and actually determine what it is you found? And that's why I was sort of driven to Himiko, somewhat lower shift analogs as a way maybe to understand what's going on. But there will be deep fields, trust me. And there will be deep fields with lensing also, right? I mean, there's this big effort to develop lensing tools on gravitational lensing to get very deep on specific objects that are picked out at random by Mother Nature rather than just an unbiased survey. Yeah.
Does JWST have a limited lifetime? Are there any consumables?
Yes. So you always design a spacecraft for 5 years because the price goes way up if you ask the aerospace company to qualify for 10. So you will hear 5 years and expected 10. But because of the rocket lift capacity, we were not going to fill the hydrogen tanks, and the hydrogen is needed for station KPNL2. And through various negotiations with Arianespace, we actually have extra mass that we can launch. And so we're going to fill the hydrogen tanks. And so the current unofficial number is something like 14 years. And so the answer is yes, but you don't look like you have to worry about it.
I have a question about, it's a couple of years before launch, a couple of years before launch, plus.
Right.
What is the status of pipelines, data analysis, and so on? Because we are not going to get the raw data, right?
So for the near-infrared instruments, the detectors are very well behaved, and the pipeline is, as far as I know, basically done for standard data. For the mid-infrared instrument, the detector is, I say our detectors have 12 bad habits, which is my way of saying that it's not that they're fatal problems, that they're going to be impossible to reduce the data, but there are things they do they wish they wouldn't do. And we're working on how to fix all those, and we will have a good pipeline. We had a review just a couple of weeks ago, but maybe not quite as good as the near-infrared, but that all has to go in by the end of this year. So well before launch, there will be quite mature pipelines. We will, of course, discover things on orbit that are not included in the pipelines, but that's just part of the way things go, right? Yeah.
So one of the pathological diseases of space missions is preparing before launch too many different observing modes that never actually get used very much, and with the complexity of all the different sub-instruments on JWST, that could go really bad. So I wanted to ask, is there, have you put effort into just sort of making a few simple observing modes, or do we in fact have like 500 different options to work through?
We don't have 500, but we have a lot because the instruments are quite complicated. And you know the reason there's vested interest in every one of those modes. So we probably have too many. But I think there's less room for mischief here than there was in some of the HST instruments that had exotic filters that did certain things that never got calibrated. We don't have anything quite like that. So I think the probability of modes that never get used is lower, but it's still going to be complicated. And to make it more complicated, we just got approved running the instruments in parallel, which will produce a lot of science we wouldn't have gotten otherwise, but that's not a big step in the direction of simplification. So yes, it will be complicated. And your concern, there may be startup problems, is certainly a legitimate concern.
George, how easy will something approaching real-time analysis be? If you're looking, as some of us would like to do, for transients, things that are changing rapidly, and you want to go from photometry to spectroscopy.
Depends on how corporate your graduate students are.
But I mean, from the hardware point of view and from the mission point of view.
So The telemetry comes down every day, and so that will be all the data nominally taken during that day. I think the latency that you're getting it will be, a day or two, something like that. Running through the pipeline may be slower, but the pipeline, the Institute is happy to release, so you would probably want to run it through the pipeline on your own. And then it really is just a question of how quick you are at getting things turned around.
One more question.
Back
Go
here.
ahead.
Hi. Given the complexity and the amount of money invested in this project, has the thought of a service mission even been talked about? I heard at some point that there was discussion about adding some kind of docking location, etc.
We're looking for volunteers.
But is it lost in L2? Like, you're just going to give up?
So, the serious answer is we were required to put some sort of fixture on so that a robotic servicing mission might be able to
Someday.
attach, but no engineering of the depth that's required went into that. So I think the answer is basically no.
No. But something has been designed into there, so in theory...
I'm not taking any comfort from that because it was sort of by direction, and nobody really thought this was a practical thing to do. And so it did not have, to figure out how to do robotic servicing of something is not something you just wake up in the morning and say, I'll put the fixtures on and we're done. It takes a lot of engineering to figure out how to do that, and that never happened. So I think we're really counting on it working.
Okay, well, if there are no other questions, let's thank George again.